This conference will now be.
And my topic is going to be, is California ready yet for advanced technologies to process residual solid waste into energy, fuels, and chemicals? This has been an issue that's been discussed for decades. As many of you are probably aware, and I'll touch on briefly, the way the legislation is set up in California related to the recycling of solid waste, there's very limited opportunities to use advanced what's referred to as advanced recycling technologies or chemical recycling. And I'll just kind of give you a sense of what I feel needs to happen if California has any chance of ever reaching a 75% or more diversion from solid waste landfills. Let's see, how do I advance this now? Oh, there we go. So who is Minette? Well, it's a company I work for. I used to work for waste management for 24 years. I retired, but that didn't stick. So I went to work for Manatt. Manatt's a large professional organization of lawyers and consultants. My area of focus is energy and the environment in California. We have the bulk of our operations in California. And so I focus pretty much on energy and environment in the West, although we do have other services. The company started out as a major health law firm providing legal and consulting services to the healthcare industry, but have expanded well beyond that in the last several years. Advanced recycling technologies, which I refer to as art, and there's an art to do this, can take many forms. The ones that are on the left, there's physical, biological, and chemical and thermochemical. And the ones that are highlighted in green are really basically all you can do in California for the most part, unless you get special compensation. And maceration, mechanical, biological treatment, composting, and anaerobic digestion, that's about it. Yet there's a whole panoply of different technologies that are being developed worldwide in Europe and the Far East, including gasification, pyrolysis, other types of technologies, which I'll talk on. So the problem is these are pretty much closed off, and for the most part, we have a lot of residual waste that ends up going to landfills because there really isn't a way to easily separate, although I think one of our speakers today are going to talk about separation technologies, which is by far and away the best thing to do. But should we use other advanced recycling and recovery technologies for materials that can't otherwise be effectively separated? And my answer is, I think yes. Advanced recycling technologies are non-incineration technologies, which this isn't mass burn. It converts non-cyclable portion of the solid waste stream to electricity, fuels, and/or industrial chemical feedstocks. Waste to energy, fuels, and chemicals was a acronym that Scott Smithline, the former director of CalRecycle some years ago, back about 10 years ago, tried to push forward the idea that maybe we should look at these additional kinds of technologies. And the reason for doing so, it would enhance the circular economy to allow these materials to be returned to useful, beneficial use within the economy. Less reliance on fossil extraction, there's greater revenue potential, and other benefits involving lower greenhouse gas emissions, maximize the recovery recyclables. They can be community sized and scalable, much more efficient and versatile. And the three technologies I really look at the most, although there's many others, are gasification, pyrolysis, and process engineered fuels that can be used in industrial furnaces such as cement kilns. By converting the residuals that we're sending to landfills to extract the organic portion to make a low carbon fuel. And right now you can do that, but it's still considered disposal in California. It's not considered recycling. And that is a problem that I think is real concern that's going to have to be addressed. And here's a complicated, but in a sense simplified chart of what the problem is. You've got all these provisions in the Public Resources Code that basically prevent you from using advanced recycling technologies because they're either a form of what's called transformation or engineered municipal solid waste conversion, both of which are considered to be disposal. There's a couple exceptions to that. For example, there is a definition that allows gasification, but the kind of gasification as defined means it cannot use any air or oxygen at all and can't have any discharges to air or groundwater, and can't produce any hazardous wastes. Well, there's few things that are possible to without any discharge at all or any kind of production of a hazardous waste. And that should not be the criteria. It should be whether or not these discharges or production of hazardous waste or other contaminants are managed within the environmental criteria otherwise required by the state of California and elsewhere. And that's the real issue. We shouldn't just simply define these technologies or these kinds of things out of the equation for consideration to help us reach these 75% and beyond to really achieve a true circular economy. What are the environmental concerns? Well, advanced recycling technology, otherwise known as conversion technologies, which is kind of a bad term these days. It conjures up a thing of dirty energy and this sort of thing. But these are not really waste to energy mass burn projects. They really shouldn't be controversial because it really would help and maximize the beneficial recovery of other kinds of materials, and glass and metals can be more easily recovered. Plastics and organics, fossil organics can be recovered to make new plastics. Don't have to be burned. They can be broke it down to the molecular level and have them reconstituted into new products. And that portion of the waste stream that is non-fossil organic or biogenic can be produced and made low carbon fuels. Is it unproven? No, most of these technologies are in widespread use around the world. It's ironic that California is leading the charge to get to a circular economy with zero waste, but basically prevents you from using these advanced recycling technologies. There's only one small remediation unit in California at Fort Hunter Liggett by Sierra Energy. And there's some agricultural operations that are under development, but nobody has had the courage really to charge us. I think really at the end of the day, as I'll probably emphasize later on, there's going to have to be a coalition gathered to really try to push changes to California statutes and regulations to allow this. And right now we have very low recovery of glass. We've got higher recovery of metals, particularly aluminum. Paper's okay, but only about a third is being lost. And the argument that as advanced recovery technologies is used once and the resource is destroyed is nonsense. All recycling is not 100% perfect, and we ought to be able to make sure that we maximize the recovery of beneficial use materials while minimizing contaminants and pollutants that would otherwise be a problem. And here's the reality, is that California has learned that recycling is more than just collection and export. You've got to make beneficial use of it. And in fact, the disposal in California, as you can see, this only goes through 2017. We're now in 2021, 4 years later, and the curve is still going up. We're almost close to 50% disposal of our waste into solid waste landfills. And unless we begin to expand the use of technologies that can be applied to beneficially use residual wastes, we're going to keep on at this no better than 50%, in my opinion, and the opinion of many other people as well. But wait, there is this thing called SB 1383. If this was in person, I'd ask everybody, have you ever heard of 1383? And there'd be a large chuckle, I'm sure, from the audience, because of course you've all heard about it. And of course, the purpose is to divert organic waste from landfill disposal to reduce methane emissions that are coming from landfills. 75% organic waste reduction by 2020. I'd ask for a show of hands now. How many people think we're going to meet 75% organic waste reduction by 2025? It's highly unlikely. And there's other issue is that word of caution, even though it's 1383 recycling, the 75% recycling, it's not the same as AB 939 diversion. And this is kind of highlighted by this Article 2 that's in the 1383 regulations. And it allows other technologies that constitute a reduction in landfill disposal of organic waste. And those the technologies include recycling centers, food recovery, composting, anaerobic digestion, biomass conversion, land application, animal feed. but also is in a new area called approved operations that reduce short-lived climate pollutants. You're going to have to, if you have such a technology in an operation, you'd have to apply to calorie cycle with review by CARB, but you can't do it until January 1 of next year, because that's when the regulations take effect. And of course, unless the regulations get delayed by pending legislation, which is being considered. So the problem is you can't really get access to Article 2 until the regulations become effective. You've got to show that the permanent greenhouse gas reduction is permanent, but it could include waste to energy, fuels, and chemicals. And you've got to show that the diversion of organics is equivalent landfill methane reduction to that achieved by composting, for example. You can get an approved verified technology. It could include gasification, could include pyrolysis, although no one has done it yet. And we won't know until you can have access to these regulations to see if that can actually be done. But the big catch, as I mentioned above, is it's still considered disposal under the California's AB 939. So it could be reduction from landfill disposal under SB 1383, but it would still be disposal under PRC if you're using some of these advanced recovery technologies. And that's obviously an issue that needs to be fixed as we move forward. And here it really is the expanded waste management hierarchy. It's not what California uses, but what's becoming to be widely used through other places in the world, in Europe and in the East, is that you have the recovery of energy and metals, enhanced recovery, but you've also included advanced recycling into the definition of what constitutes recycling. And right now, California, pretty much with respect to organics, only allows composting and anaerobic digestion and a few other things as well, but you really don't have access to some of these advanced technologies. And by the way, this slide and a couple others I'm going to show I obtained those from Dr. Rachel Meidel with Rice University, and she was with the Center for Energy Studies, and she makes a very compelling argument and has been coming more and more to California to try to convince the policymakers in California, including CalRecycle, including the Recycling Commission, that they need to open the doors a bit to allow some of these advanced recovery technologies to maximize the beneficial recovery and use of all materials that are found in the residual waste stream. And here's the plastics problem and particularly as pointed out by Dr. Meidel, is that the US and Canada, 90% of plastic waste ends up in a landfill or is incinerated. And that's basically 34 million metric tons, which cost billions in disposal fees. It's a lost commodity value from unrecycled plastics even greater. And really, there isn't anything that can really be done with plastics other than to break them back down into the component molecules and make them into new products, or if it's low enough carbon, doesn't raise greenhouse gas emissions concern, use it as a source of energy. But that's pretty much for fossil plastics, in my view, need to be limited to only recovery of the molecules for purposes of making them into feedstocks to produce new products and materials. And today's supply of recycled plastics just meets 6% of the demand. 94% of plastics there is not effective use for. And that really causes problems, as is really pointed out in this next slide, again, courtesy of Dr. Rachel Meidel, Rice University. California has these competing priorities. In fact, they've always had competing priorities. For example, zero emission vehicles by 2030, and hope to have all vehicles, including trucks and buses, everything zero emission vehicles by 2045, if not sooner. And it's plastics are the second most commonly used material to make low emission vehicles. 50% of the vehicle volume, and probably is going to be increasing. And there's 39 different types of polymers and plastics that are used in zero emission vehicles. And current plastics recycling of plastics in cars is very low quality. And so you really can't access it without taking these advanced technologies and breaking the material down into its component parts and reconfiguring it into new products and materials, hopefully new zero emission vehicles. You've got this 100% requirement also for carbon emission-free electricity by 2045 or even sooner. There's an increased demand for complex multi-material plastic for wind blades, for solar, for electrolyzers, but only option really for most part of waste from these kinds of activities is landfill and incineration. So increased mining to produce more minerals is going to produce more waste. Reliance on offshore supply chains for extracting and processing. All this can be addressed if we could have access to advanced recovery technologies to recover the molecular value of materials that are ending up in the residual waste stream. And then finally, as we all know, we've got 75 waste reduction and recycling goal for everything, including plastics. How is that going to be achieved? And you talk to Dr. Meidel and you talk to most other people that are familiar with the ability of these technologies. It can't be done. We cannot reach 75% recycling of everything unless we open the doors to begin to accept some of these other technologies, as long as they are operated and constructed in conformance with California's other environmental laws, whether that's hazardous waste laws, whether it's air quality, whether it's water quality. That should be the criteria you're required to meet, and not try to establish definitions that are immediately exclude these kinds of technologies from being considered recycling or appropriate recovery technologies. So I'm finished for that. That's kind of the lay of the land as I see it. I think we've got a lot of work to do with the legislature and the administration and our friends in the environmental community to try to get them to understand that we, in order to get 75% or more, and really create a true circular economy, we're going to have to open the door for advanced recovery technologies sooner rather than later. And it's been a long time coming, and we still got a long ways to go. So hopefully the folks that are going to be coming after me in today's session will hopefully open the door further for some specific technologies that will allow the enhanced processing and recovery of residual solid waste. Hold your questions unless Tim wants to do a couple now, but I'll be happy to wait till the end of the entire session, and I'll stick around until the end of the program.
Thanks, Chuck. We are running a little long, so I think we're going to hold that question back. If you see it there, you can be ready to answer it later, Chuck. It's with respect to growing concern over PFAS. So let's keep going now. It's time for Michael, and we're running a little long. Sorry about that, everyone.
Good morning, everyone. I'm going to go through a process that TORXX developed over the last year to repurpose typical MSW fines that are laid up to now, most of it going straight to landfill because too hard to upgrade or turn into a usable product. So basically is using our Polarizer technology, we've been able to fraction enough the material to allow recovering up to 70% of its organic content. That material is coming from the front end pre-screening of mixed waste, and it's still really rich in organic, especially on the West Coast or in regions where it's all in the same bin. So by recouping that, by processing that material and being able to recouping the organics can easily be mixed to compost, feedstock, or used for land application or any organic application that's available to on the market. So basically how it works is we solely relying on an aerodynamic physics that we develop. Is the machine is not grinding or cutting the material, the machine is agitating the stream into vortices, and basically because the matter against matter material, once it gets into the machine, liberates the organics, pulverize any aggregates that's in there, like you'll find a lot of glass, you'll find some little rocks. Those will turn to silt, which is in fact beneficial for compost. But The other big advantage is the softer material. Think about juice pouch or chip bags or any of that. Those will not destroy, so you can, after the process, after it's been processed through the pulverizer, you can easily classify it and screen it with conventional technique. So just to give you an overview, we'll go through just a quick video of installation we have in place, which are actually processing those mixed waste fines. So that's the actual feedstock that was going to landfill previously, which is all the 2 inches minus material coming from the front end. So we're metering that material to the machine at a pace that range between 12 and 14 tons an hour, which is pretty much meet the requirements of medium to large scale mixed waste sorting facility. So all that material is introduced all together into the machine. Then the pulverizing effect, the pulverizing action happens from there. That's the output of the machine that we are migrating to a screening media like you see here. So all the oversized fraction is mainly trash, or mainly things that are not organics because they didn't self-reduce. And if you see on top here, that's the organics material that being homogenized and size reduced by the pulverizing process. And on the bottom, you have your actual residue. So up to now, we achieve pretty much 70% of the inbound weight of that 0.2 inches mixed waste. Pretty much 70% by weight comes out in organics that can be mixed with compost or used for land application or any organics fraction. So that's what the organics material looks like at the end of the process. That's the screened material that we already seen people going for composting with it. So you see it's really granular, it's really consistent in size. So what we also figured with the machine is there is multiple other applications that we can run, or multiple other type of feedstock, like shingles, for instance, compost overs that are actually discard because the difficulty of removing the contaminants, land clearing debris, C&D fines, which also been a topic the last few years. So by processing it through the pulverizer, we actually ease by much classification of material and repurpose of good material. So that's pretty much the concept we had in production. And anybody who will attend Waste Expo, feel free to visit us. We'll be there for the entire expo.
Thanks, Mike. That was pretty good. Appreciate it. We've made up some time now, and I still think we're going to roll the comments into the end just from a standpoint of efficiency. But take a look at the note there from Andrew about plastics. Mike, let's pick up that question at the end of the set. Yep. Get Eric going now, if you don't mind.
All right, thank you very much. I assume that you see this now. So we're Waste Robotics. The presentation is about two methods of collection for the organic. So what we call organic co-collection and organic cart collection. So we're going to try to show the difference. We all know that the overall target for diversion of organic from landfill is trying to limit the fugitive emissions, mainly for GHG reasons. Most people know that, or most of the systems right now about targeting, trying to go and collect this organic is about a three bin system. So we have the garbage, we have the recyclables, and we also, usually people will add a third route for going and collecting the organic in a third bin. What we are proposing is that instead of deploying a third cart and a third route, we distribute bags, and we ask the citizens to put the organic in that bag, let's say the green bag, and drop that green bag within the garbage bin for co-collection at the same time as we're collecting garbage. So it seems to pause here. Sorry. Well, you get the idea. And thereafter, the idea is that we're extracting the organic from the with a robot. So the idea of picking up with a bag system is hard to implement if you don't have like an automatic way to remove it, and it's fairly difficult to remove it. So you cannot. We have a lot of recycling pains right now into MRFs and others. So try to foresay, like, we're going to do bag collection and we're going to remove these bags from the MSW with people just doesn't make much sense. So what we're coming in is we have developed technologies to be able to recognize these bags on the belt, be able to capture them with great accuracy, and be able to reconfigure systems. So that's what robotic sorting comes with the bag system and robotic combined becomes really interesting, because now you have the ability not only to save on collection, but also when you have to sort it out, you do it very efficiently through a robotic system. So I'll try to show a video here. So this is a system we have in the incinerator in Quebec City. People put their organic in that little green bag that you see there, and the robot detects it and goes and pick it out. So this is MSW without any screening, without anything, straight out of the tipping floor, being loaded right onto the line, and the bags being picked. The rest of the materials going straight into the incinerator. So this is in a nutshell what this shows. So what are the value benefit and what does it do? What we have observed, like in Quebec City, they've run different pilots and compared the efficiency of carts versus bags. What we discovered is that you get a much better, higher organic diversion, because people participate, because we distribute these small bags, they're kitchen counter bags. People participate because it's clean, because it's easy to use. People just throw their stuff in there to tie it up and to put in their garbage bin. So the overall, there's a lot of interest from the citizens to participate because it's easy. The cost of collection is reduced by about 50%, because if you're going to run a third route for the next 20 years, for example, compared to just distributing bags and running the robot, the overall difference is about 50% in saving. And you can appreciate that if you're collecting more organic and you're not running a third route, the comparison between the co-collection, organic co-collection system and the conventional cart system, you have a very high reduction in GHG because you're capturing more and you're not running all these trucks. And the ease of use make it more participation and higher overall diversion. So about the technology, just in a nutshell, what we do at Waste Robotics, we develop robots. So we have like computer vision systems. We make scanners that will scan through the material. We look at the material through different types of cameras, hyperspectral, 3D, color. we could then be very precise in that identifying products. Like this is very difficult to do with AI and or humans, but with hyperspectral signals, we're able to classify this properly, and then we dispatch this to different type of robots. We're sort of agnostic to the type of robots. Depending on the job, we'll use large robots, small robots, depending on the payloads. So we have this sort of ability to tailor the solution. And this is the application in Delano. I'll come back to this a little in a few minutes, but this is collecting organics, compostable bags. So we can take an existing MRF and convert it like this. So we are really into tailored solution. So the ability to adapt. So depending on the situation, we'll use different type of robots. We'll use different type of sensors and different type of grippers, because the overall robotic world is all about pretty much sensing and picking it up. The arm is kind of a commodity that we use to move that gripper in space and go and perform the picking. Back to the organic, we've come across different situation. For example, this is in Dunkirk in France. The city there just says, okay, this is going to be easy. You're going to pick out yellow bags and with your robot, but actually the bag's not yellow at all. It's actually, when it's filled, it's just anything but yellow. So it became quite a difficult situation. That's when these are the real life conditions that we're in right now. And that's where AI came in to help us, because just on color or shape or any of this is very difficult, but we're actually able to collect these bags. Now, if you pay close attention, actually in Dunkirk, we're not picking up organic bags like we are in Delano in Minneapolis. We're picking out recyclable bags. So that's another spin on this, is where we have the ability. So what Dunkirk is doing now is their citizens putting the recyclable in a bag, and starting beginning of next year, they're going to have both bags. They're going to have an organic bag and they're going to have a recyclable bag. So that's going to allow them to collect all garbage, recyclable, organic, and garbage in only one truck route, which saves a lot of money, and GHG, which is one of the key driver in this situation. The other interesting thing about bringing robots to the situation is that it's first time we actually have recording eyes on the conveyor. So not only can we teach one robot one trick and it can exchange it to another robot across the world. So if I'm picking out blue bags in Delano and run the same bags in Montreal, the learning doesn't have to be redone. But more importantly, not only are we picking out bags and looking for bags, we record everything we do. So we have the ability to replay the tape if you want and go reanalyze what's on the belt. And that data now, it's gaining very interesting, because people are interested to know, okay, besides the bags and besides whatever you're picking, what else is left on the belt? So that allows us for running statistics and composition analysis to sort of assess the overall efficiency of the system and everything else. And the other thing we do at Waste, we're also, some of our clients come to us, are like, yeah, we don't have capital, what have you. So we're offering what we call sorting as a service. So that allows for people to basically, we will make the capital investment if they commit to a contract, and basically they pay by the usage of the robot. We have a calculator online if anybody's interested. So just to go back on organics, so this Quebec City is doing organic waste collection, co-collection. We have Randy's Delano. As I said, Energipol in Dunkirk is doing right now recyclable bags. In Delano, this co-collection system has been there for a long time, but our robot was introduced there in 2018 or 18. So in this situation, this is in a transfer station, so straight out of the truck, they load the line and the robot just picks out the blue bag. In that case, that blue bag is actually a compostable bag, so it doesn't need to be open. It goes straight to the composting site. and it's BPI certified, so actually it degrades within the 70 days and all this. So it's a really good system because not only diverts from landfill, it actually creates very good quality compost, because when people make the gesture of putting it in the bag, actually the quality of what's in the bag is really high. So that's an interesting thing to note. As I said, we not only are we doing bags, we're also doing other types of system like construction, demolition, debris, and recyclables. And we also do more funky stuff like this one here in Quebec. We do styrofoam sorting, and this is Dunkirk now, but they ordered another line with 3 robots for doing the additional the food waste as well. I don't know how I'm doing on time. Quickly.
You're doing good. Very good. Thank you, Eric. Yeah.
Right. I just don't want to. I don't want to bore anybody.
These statistics look like they're important. Why don't you go ahead and run through them?
Yeah. So we sell systems. We're a company out of Canada, but we selected FANUC robots. They're the biggest FANUC robot manufacturer in the world. They offer a very large network of service. So when we sell a system, obviously people want to make sure that it runs. So we have a very quick response time for any fixes that would have to happen on robots. Quickly about us, we've been doing this for 5 years now. I specialize solely on robotic sorting, primarily in the organic world. Most of our references are around organic, so we're pleased to have a chance to talk about it in California now. All of us have a lot of experience in waste, in robotics, and or in computer vision. So we're still we're a small team, but a very passionate and solid team. And if we've received a lot of distinction because we're coming to market with a very innovative approach, very different from anything else that all the others are doing. We're really into tailored solution, and especially with the organic, we're really keen. It's picking up really heavily here in Quebec and in France, and we hope like in California or in other jurisdictions where they're driven to divert organic, we could actually make a difference there. So yeah, that's what I had to say.
Thank you, Eric. Good stuff. Appreciate it. A lot of interesting stuff in this presentation, or these series of presentations. Let's go back and pick up the question. Chuck, the first one was aimed at you about PFAS and how it's what the destination and how that's handled in the current legislation. Why don't you can you pick that answer up? It looks like Chuck is still silent.
There we go. I got muted.
There you go for it.
Yeah, PFAS is an increasing problem because you're seeing more and more PFAS showing up in the waste stream, although PFAS is being discontinued in a use in most products, but there is still a presence of it. And the problem, of course, is that it gets into landfills and it could potentially show up in the leachate coming out of those landfills. And if the leachate is then sent to a wastewater treatment plant, it probably goes for the most part right on through and out into the receiving water. The good news, I think, is that PFAS has pretty much been shown to be able to be broken down into its component molecular parts in through gasification and pyrolysis technology. US EPA has been doing a lot of work on this with a lot of waste streams, including wastewater, treatment sludges, and solid waste. And they're finding that for the most part, they're very effective at getting rid of the PFAS and breaking it down into molecular component parts that can either then be screened out or can be potentially safely incorporated into whatever is going to be used by that material. So I think that's another good reason to take a look at some of these technologies, these advanced recycling technologies, to help address a wide variety of problems, and not the least of which is finding a solution to PFAS. And admittedly, more work has to be done, but I feel very encouraged about the results that I've seen so far.
Thank you. The next question looks like Andrew's actually, Andrew asked her, but it looks like Terry answered it maybe for Mike. I don't know, Mike, if you want to expand on it, the answer is written there from Terry.
Yeah, I just want to add a little bit on what my colleague is. Basically, you have to understand through the process the plastic content that you commonly find in those mixed waste fines. Most of it is ductile, means the machine does not attack these plastics. So most of the plastic films, like PT, HDP, those malleable, those flexible plastic, they are easily screened out before the finished product. It is true that you will find some bits and pieces of more brittle plastic, like polypropylene, for instance, or polystyrene or hard polystyrene. But based on all the tests we did and the analysis we got, it's well below the acceptable rate of the existing composters, throughout the U.S. The plastic content is minimal at this point because most of the ductile does not even make the cut to the finished product.
Thanks. I noticed that your video, or you're showing the pictures there. It appeared to be a pretty pristine organic separation. So that's interesting.
Yeah, it was above our expectation.
Interesting. I don't see any more questions for Eric or Chuck, but if there are any, we're open to hearing. And if you want to now just unmute your mic now that we've gone through the hurry of it all and we're at the final stages. If you haven't entered a chat box, which I'm not seeing anymore, Mike. That's it, right? Yeah. Open to more of an open discussion. Anybody here want to unmute and just talk for a bit?
Tim, if I may, about what Chuck mentioned on these alternative solutions like gasification, pyrolysis, on all this. We've been in conversation with some of these people because the ability to potentially remove the organics ahead of even incineration to sort of stabilize or get a better PCI, and because most of these processes are often impacted by the level of how wet it gets, so we can encapsulate and capture some of the organic right on the front end. That limits or that stabilizes a little bit that sort of moisture content and makes these processes more stable and or more efficient usually. So this co-collection actually has benefit on front of incinerators or any other advanced technology sort of conversion systems.
Yeah, absolutely. I can appreciate that. And also I've been a part of this conversation Chuck mentioned for at least a decade, and it's one that is it's just not going anywhere. So I hope that Chuck's your presentation can be floated by enough people to stir the conversation. Eric, I have a question for you. Given the potential savings of one, if not two, trucks off the road, the greenhouse gas emissions from that, and then the savings that could be passed into the robotics system, do you have any kind of have you done any economic analysis of these things? Well, first of all, environmental analysis, because there's a huge reduction in the diesel or other kinds of emissions, and then the economic side of it.
Well, the most simplest way to let's say you want to roll out a third bin for organics, for example. The price of the robot is the price of the bins. So it's basically you can buy yourself a robot or buy yourself a bin. Thereafter, of course, with a bag program, you have to distribute the bags, so you have the bag cost and the operation of. But that's when I say the value proposition is that the overall cost is 50% less. That's what I mean, because actually operating the robots and rerunning the material compared to running all these routes, it's price. So and it scales pretty well. It's amazing that in very dense areas like multi-dwelling, this capture of organics gets really good because it's very difficult to do with carts, for example, and so it's very efficient in dense areas where there's multi-dwelling. You capture more organic, and it's also very efficient when it's not dense at all, because then if you have a very spread out bunch of houses, the distance between them is more, and so then your cost of actually lifting that cart gets really high. So then the system shines on both ends. In the middle, it's a little bit less, but mostly it covers. So I don't know. It's a fairly complex thing because this technology sort of spreads collection and sorting. So the economics are not. But the simplest way to see it is that you would invest about the same amount in carts versus the robot.
Thank you. Reopen the invitation to anyone else. Here's a new one.
Well, this is Chuck.
It's aimed at you, Eric.
Oh. Tim, this is Chuck. I was just going to add a comment on. I mean, I really fully support the idea of doing as much separating as you possibly can before. That should be the first step, getting the material separated. But if it's uneconomical or can't be done, then advanced recovery technologies such as pyrolysis and gasification can be used for the mixed waste to separate the material down to its molecular components. So, but I totally support the idea of using these separation technologies as much as possible to be able to do that ahead of time. I'm always a little nervous about putting things in bags and thinking that all the stuff in the bag is, for example, going to be organic, and someone's not going to slip in a can or a bottle or a ceramic or something like that to cause a problem. I know I've been living with my wife for many years, and I work in the solid waste business continuously, and she still has a hard time figuring out what can or cannot go into the various bags that we have in Davis, California. So I'm always worried about how that's going to happen. In fact, I'm curious to know if you gentlemen that are separating out these organic bags have any problem with residual contamination of people putting the wrong things in the bags.
The experience has been less than 3%. Yeah, of course, there is some people, and the size of the bag is also very important. So if you're giving, for example, in some situation, they're giving smaller bags for kitchen catchers with a specific bin on the counter. That limits the amount of stuff that people can put in these bags and limits the utilization of that bag for other means. So the size of the bag and the type of bag is quite important. And when we go, also there are some commercial aspect to this. So actually they will roll out bag co-collection program for bags in the commercial sector. So, and in this case, again, because these clients actually are aware and they train their staff, but usually it's less, it's about 3% in Quebec anyway, and some in France, 3% in the bag, where if you give them a large cart, it will go up to 10-12%.
Makes sense. That makes sense. Thanks.
Or way higher elsewhere. Look, Michael, looks like there's questions for you about the feedstock that you were processing.
Yeah, the feedstock that's processed at that location is basically, it's a dirty MRF. So it's a single route collection. So it's dry MSW, mix of garbage, recyclable, organics, and seasonally you get the yard waste as well. So technically, what happens to the wood itself is if it's limbs or grain limbs or small things like that, those will tend to come out with the rejects, the overs material. They will not size reduce enough to make the cut and goes with the compostable material. But the yard clip, the grass clippings and all that stuff get blended pretty well with the organics, which is also a plus for compost. And if you happen to have larger branches or stuff that it's drier, harder as far as wood content goes, it will size reduce, and a good chunk of it will size reduce enough to go with the unders, with the accepted material, which is a compostable material. I don't know if it answered the question, but
I think I got it. It's not actually a separate collection bin. It's actually fines out of a mixed waste MRF, and then that's how you're
fines out of the mixed waste MRF
Yeah.
that we're processing and recovering all the compostable or organics material content into that fractions of the incoming material at the facility.
Got it. Thank you. Well, I'm not seeing any more questions, and it's been a very helpful dialogue here. I really appreciate everyone sticking around a little longer. We're almost out of time. I'd like to say special thanks again to Cecilia for Rios for hosting again, as she's done for many times. Kimberly Cook has been on the team and not here today. Ruth Abbey's here. Thanks, Ruth. Appreciate all your help. And anyway, I just want to say again thanks to all, and appreciate for how this has gone out. And if there's any more questions or whatever, have an email to us, and we'll try to field that as best we can. Anyone else? Anything else? Okay.
Thank you for putting this on. Very good.
Happy Friday, everyone.
Thank you.